Hello and welcome everybody. Thank you for joining to our channel Petrosoftware, learning more new technical skills in oil and gas software. So in this lecture, I will share with you more advantages from using Excel sheet, and by the end of this lecture, you will learn how can analyze the data using Excel sheet and how can we generate history matching technique as we see here in Petrosoftware. This case study in this case study we can see here, and if you join it to reservoir modeling course, you see the analytical method. It's the relation between the tank pressure, reservoir pressure data with cumulative oil production. We can see here calculated oil production. What the mean of calculated oil production? That's mean material balance. Again, calculate the cumulative oil production and then compare it with observed data. So we can see these points is the actual pressure and cumulative oil pressure measurements, and this line is predicted by material balance technique. So this is the history matching technique. We have two types of history matching: analytical and graphical. So today in this lecture we will learn how can we generate this graph and this plot and how it works in using Excel sheet. To understand more deeply, this lecture will be very useful to students who still study in the petroleum engineering courses. So we will learn that's one of the advantage. Also we will learn how can we generate graphical methods with different methods calculating the original oil place for our case study using Excel sheet. By the end of this lecture, you will learn how can we go deeper and understand more, increase our knowledge, and learn more about mathematical equations. This equations involved in the software. So always the software is just only a tool. You have to understand how it's work. So in the one of our previous lectures, we learned how can we generate analytical drive mechanism by material balance. So today we will learn more about that. Here in my case study, I have reservoir data. Initial reservoir pressure 10,535 psia, and the reservoir temperature is constant. Always the reservoir temperature is constant, especially, and that's the assumption of material balance technique. It's 212 Fahrenheit degree, and we have a reservoir area and reservoir radius and initial water saturation and the bubble point pressure and formation compressibility. Here we have our production history. We can see the time the production starts in May in 2003, and that's the time of days and the initial reservoir pressure, and then after the production, cumulative oil production increase, the pressure is dropped. So we need to have some more information about these numbers. And first of all, we will start by reservoir pressure. We can see here this is the reservoir pressure. It's constant initially, then still decrease, but we can see here the increase of the pressure at the last point. The pressure is 8,380. It's still above bubble point because the bubble point pressure is 8,104 psia. So this is the first information we can get from this plot: pressure versus time. Also we can see the trend of the pressure is supported by, we don't know what's the energy supported the pressure. We know from our study maybe we have water influx, maybe we have water influx, or any injection, gas or water, but we will look more. Also, we have oil production, gas production, and RB, gas oil ratio, produced gas oil ratio. We can use one of them, gas oil ratio or production. RB, it's divided by gas production divided by oil production. We know above bubble point it must be equal to RS. We know RS, that means above bubble point it's 1417 stock tank standard cubic feet per stock tank barrel. This value will be constant until bubble point pressure, and then will decrease. So from this value from BVT, always oil formation volume factor, and RS and beta G and other fluid properties comes from BVT lab. So that can be confirmed with RB because RB comes from production. So always when the reservoir pressure is above bubble point, it must be constant. We can see here initially it's no big difference here. Then after the production we can plot the time versus RB. Sorry. And that must be confirmed. Yeah, we can see here it's nearly constant. I plot this with RB, but in 1000 stock cubic feet per stock tank barrel at the same, but with here in standard cubic feet per stock tank barrel. We can see here it's approximately constant. That's the initial points. We don't need this initially, but after the pressure is dropped and we can take that an average, so we can see here it's constant. If it still increase like this, that means the reservoir pressure is below bubble point and the RB will be increased, but here it's approximately constant, no big difference between these numbers and RS. And these two plots very important, help us understand the classification of our reservoir, and we need to see the water production. It's one of the most important parameter we need to see how it's look like. Oh, we can see here the water production is nearly constant here. Then at this time we can see a huge volume of water produced from our reservoir, and that's the question right now is when we compare that with, let's see, the pressure, and yeah, we can see here at this time about yeah, in 2005 and 5 here, the same time we can see here all of this period is nearly constant, the pressure here, and that's the question right now. No big difference here in the pressure points versus high increase of water production, and that's from this plot we can have an idea about water influx. So what the sources which can increase the water production, it's water influx. Also we can see here the pressure at this period, it's nearly constant, and this happen only in reservoirs that have strong water influx. We know when the huge volume of water invaded into the reservoir from the aquifer when we produce some oil or gas and water, and the output from our reservoir equal to the input into the reservoir, the pressure will not change ever, because the huge volume, and that's the assumption of material balance. We can this is very important. We can see here the material balance assume our reservoir is a constant tank pressure, so all the fluids will be comes into this tank. So at the initial, if we assume the reservoir pressure is equal to or if our reservoir initial condition, we have a gas cap, so this is the total volume of reservoir, include both oil and gas. So this is the volume of gas, and this is volume of oil. The ratio between these two volumes is equal to M, and when the pressure is dropped, the huge volume and when the pressure is dropped from initial point to below bubble at any point below initial reservoir pressure, so we can see here the water influx invaded into the reservoir. We can see here the difference between this expansion for oil and gas and water, which is invaded into the reservoir. The difference between them, the expansion and the initial state, is equal to the production. So if we produce a huge volume, for example, let's say the oil production is and the total volume of 100, for example, 100,000 barrel of total fluids. So if this number 100 entered into the reservoir from our aquifer, the pressure will not decrease, because we assume here the reservoir is constant. The reservoir volume is constant, bore volume is constant, doesn't change with time. And that's simply the material balance calculation, the expansion volume after the pressure is dropped minus initial state. It will give us the production. This is the general equation for material balance. We can see here in this part is total production, oil, gas, and water. And here the expansion of oil and gas. And if we have a gas cap, we can use this theorem. And the compressibility of water and rock, because it have an effect on the reservoir, and we will see that how can we apply it in graphical method. The assumption of material balance is to be a tank, as I explained it here. The tank is very important because we need to fit all the fluids here, and the total volumes comes into the reservoir. And the second one is homogeneous. The reservoir modeling always, that's the difference between reservoir modeling and the simulation. In material balance, we work with reservoir modeling. So all the properties, reservoir properties, have a uniform thickness and porosity and any other properties for our reservoir. But in the simulation, we can divide our reservoir into small grids. We can work with each grid, enter the properties for each grid, and that's the huge difference between the two methods. In material balance, we work with analytical, but in the simulation, we work with numerical solutions. The reservoir temperature and pressure are uniform distributed. So let's start our practicing here. We understand all of these about pressure and water production. So the first task I need to understand right now is my lecture today is about how can we generate and work with analytical method using this plot. So I need to create a plot an Excel sheet, pressure versus cumulative oil production. So this is the pressure and the cumulative oil. This is the actual pressure and cumulative oil pressure measurements calculation. I need to change this exit in x-axis. It will be cumulative oil, and in y-axis I will use the pressure. I need this plot. It's very important to add some curves here to compare between actual pressure and cumulative oil with the calculating point. So I will name it as analytical method. Here will be the pressure, and here okay. This line will be for observed data, means the actual data we have from our field. So the material balance, we need to calculate the original oil place and water influx volume. Then we will add another plot, another curve here, and we will compare between these two curves. If we matched these data, we can assume our values, original in place value and water influx is right. And if we miss the match in here between two curves, that means our result will be wrong. So first of all, I need this analytical method. And I will start by using straight line solution method to material balance equation. This by Havlin and Oda method. How can we convert this general material balance to use as a straight line? So here we have a term of F, means the total withdrawal from our reservoir, oil and gas and water, all the productions equal to F, and that's changed with time and with the pressure. And here's the expansion of oil. Okay, here the expansion of oil changed in the volume, and in gas and oil. And here the change of volume of gas, expansion of gas when the pressure drop, and this is the effect by water and rock expansion with pressure. So in case 1, I will practice that right now. I will assume undersaturated oil reservoir, and that's our case. Reservoir pressure is above bubble point, so our reservoir is classified as undersaturated, and no gas cap. That's normal because M will be equal to 0. So I will delete this from the general material balance. No water influx invaded into the reservoir during the production life. So here in the first assumption, in this case, I will assume we don't have any water influx invaded into the reservoir. And also no expansion of rock and water when the pressure drop. So this general material balance, after add all of these terms here instead of this, so the material balance equation will be like this. So I will assume no water, no gas cap, and no effect of rock and water expansion, and no water influx. So simply this case will be if that the total production equal to our value of original oil place will estimate it now versus the expansion of oil. So we have these two this is the linear equation, simple equation, y and x, and the slope will be equal to our original oil place. So I will practice that right now, and we will see the first value of our original oil place for our field. Okay, now I need to use the first case. Here I used the same equation for if I calculated here. You can use it from this equation. You have cumulative oil and oil formation volume factor and RB and RS, and you have water production. And this for expansion of oil. So I need to use and calculate a plot for F and epsilon O. And the slope will be, yes, I have to check what's in the X, F, and epsilon O will be on Y. That's right. So this is the first case, case 1. Now I need to calculate the original oil place from this plot. YF or barrel notes here the value of original place will be equal to the stock tank barrel, because this is when we can see here in this case when I divide to calculate the original place, F divided by epsilon O, so F in barrel and epsilon O barrel per stock tank barrel, so barrel will be cancelled with barrel and stock tank barrel it will be the unit for our original oil place. Now I can see from this plot, it's very important, we can see here this is the increase in some times, but it's not the straight line. So if this plot is a straight line, that will be a very good indication about we don't have any water influx. Okay, that's the important thing you must understand. But we can see here this increase and increase. We cannot find the straight line plot here. So our slope value will be not a very good value, and I need to add the trend. This equation is a straight line method, so I must here use this linear, yes, and I need to show the equation, yes. Here this is the value. I can add some changes here, yes. This is the linear equation, y it's equal to f here, and that's the straight line method. We cannot see the match between this equation and our data is not equal to each other, so we have a difference here and here. We can apply this equation y equal to f and x equal to epsilon O, and this value in this case equal to the original oil in place as in this equation. This is the value of n, but this value of original place I will add it here, n f versus epsilon O this value is equal to 6 billion stock tank barrel. I need you to remember this number, it's very important, and then we will compare that with another values. This is the value of original oil in place by using this graphical relation. Yes, this is N1. I will name it as N1, and I will calculate another different value N2 for case 2. Okay, so the first guess for our original in place is equal to 6 billion stock tank barrel. Alright, now I need to use and go to the next case. I will put this here, case 1. What's the case 2? Here in the first case, case 1, I assumed no effect of rock and water expansion, and that's wrong, because our value original place estimated right now, we will compare that later, assumed no effect of rock and water expansion, and we know this rock and water expansion effect on our reservoir, effect on our production, so and also as well as the water influx. So I remove this from our equation and also cancel this point. So in the next case, we will see undersaturated oil reservoir above bubble point, no gas cap, and that's because reservoir pressure is above bubble point. And we will assume also no water influx invaded into the reservoir. And here in case 2, I will include the expansion of rock and water when the pressure is dropped. So I will cancel this water influx and M, and I will add the rock and water expansion. This sum of expansion of oil and total expansion of rock and water, this is the more realistic than the last case if you assume no effect of rock and water expansion. Then if it's the total production from our field, so this together will be x-axis and in y-axis will be F. So again, I will use this plot to calculate the original oil place, then I will compare that with my case. So case 2, here I have assumption, assume expansion of water and rock. I used this equation, you can review it. Yes, I use this equation. Now I add the rock and water expansion and initial water saturation and the change of the pressure. So now I need to plot F versus both epsilon O with some of these two terms. Then we will calculate the second value for original oil place. This is the case 2. What's in y-axis? As usual, F, and here epsilon O plus minus stock tank barrel. Okay, now I need to the same behavior we can see here as in first case, but I am looking for the value of original place. Yeah, the value change it. I know I need to of course is changed, and that's the relation F plus. The question right now is why the value of this number is equal to 200 million. It's decreased. A huge volume, a huge difference between these two volumes. We can compare that. I can compare between this number and this number, a huge volume, to 200 million stock tank barrel. That's a big difference between these numbers. The difference is equal to minus a huge volume of oil in place. So the question right now is why the big difference between these two values, what that mean, and how that calculated by material balance and using just only the rock and formation compressibility. And that's the most important thing you have to understand deeply. The material balance is a volume equation. So here, if you delete or remove any drive mechanism for your reservoir, so the value of original place will be overestimation, and that's very important. So in our case study, in general, we don't have any water, any gas cap, so that's acceptable. But here in the rock and expansion, we assume in the first case we can review more about this drive mechanism. Here in rock and fluid expansion, in the first case, we assume no expansion of rock grains and no expansion for the fluids. That means we have initially water saturation. It's about 30% of total bore volume. So when we assume we don't have any expansion of rock and water expansion, so the material balance, because it's act as a tank that's constant bore volume, so the rock in the first case does to change and don't expansion. So this expansion, the difference between the expansion and initial point, is must be equal to production. So here in the first case, instead of this expansion of rock, the material balance would fill it with oil. So any expansion of rock, and that's depend on the rock compressibility and how much volume of water initially in the reservoir. So if the initial volume of water is a huge volume and more than, for example, more than 50% of pore volume, and the rock expansion have high expansion, that will lead to a huge volume of expansion of and the value of original place, it will be very, very high, as in our case here, a huge difference between these two numbers. But when I assume in the next case, case number 2, yes, I have an expansion of oil and water and rock, so this is more realistic than the first case. So less volume of oil will be in the reservoir because the sum of changes in rock and water. So now I have two cases. We have more information about, we have an effect of rock and fluid expansion, and we have two values of original oil place. This number is more realistic than the first number, but still have a high uncertainty because until now we don't have any water influx in the reservoir. So from this we can predict if we have another different effect of drive mechanism, the value of original place will be decrease more and more, because instead of this value, a huge volume of water influx invaded into the reservoir. And we will see that in the next minutes. The next point I need to share with you here, it's about completing our case. Now we need to classification of the reservoir. We need to understand if we have a water influx really in the field, in the reservoir or not. So how can I diagnostic that and understand more? This plot, it's very, very important. We have to plot in y-axis F divided by total of epsilon O and epsilon water and rock expansion versus time, or I can use the calculated or measured of cumulative oil production. In the case I will get one of these three curves. So if this relation is, we can see here, it's a straight line A, and that means the horizontal line, the reservoirs, we don't have any water influx, and if increase sometime then decrease in case B, that means we have a water influx. And if C, also we have a water influx in these both cases. But the difference between B and C, B, that means increase of water influx sometime, then decrease, that means maybe the outer boundary have been filled and act as a finite acting. And if C is increased more and more, that means the strong water influx, and that may be not still infinite acting, that means maybe the water influx connected with another different source, seawater. That's a huge volume of water connected to our reservoir. So we need to now interpretation this cases, what's the case from A, B or C. Now we will go to this, the next plot. We have cumulative oil production and time, and this is our relation in Y, and so I need to plot in Y and in X, and we will see how it looks like. I need to check X, what's X and Y. This is X, yes, and in Y I have, yes, that's good. Because always the first numbers here, it's maybe have high uncertainty, so I need to decrease this and to see the good plot. Yeah, always the first points cannot have a high effect on our reservoir. So from this I can decide how it's look like from compared with the original case. I will put that together here in Excel sheet to see if we have a water influx, and that's of course we have a water influx because the line is increased like C. I don't think so, because maybe after this will decrease, and if I have more data this will can be more clear, maybe B or C. So still I don't have a good information about this, but there is a water influx in our reservoir. So what I need to share with you, this plot classification of the reservoir, if we have a water influx or not. One of the most important technical plots help you a lot to diagnostic and have more information if you have a water influx or not. So we can see here this increase. Now I will assume still I don't know more information if water influx have a strong water affecting by that, and or maybe at this point this is the decline in the curve, maybe act as a B. So here we have a huge difference between B and C. B, as I said, this is the finite acting. This is the water influx will be limited for and have high effect, then dropped. And if increase more and more, that's infinite acting, means strong water influx, and will have more effect on the reservoir performance in the future. But here in the future, this line will not have a high effect. Maybe you after this time you will need to add some additional artificial lift, water injection to support the pressure. Okay, so this plot is specification of our case. Now step by step we are going to understand more and how can we analyze the reservoir, and I will add this. So at the last point we still don't understand our reservoir have high water influx or not. So what's the next? Campbell plot, one of the most important technical plot, have more information about this. So by using this plot, different parameters in y and x, we can have more clear vision about the water influx, if it's high, strong, or moderate, or weak, or depletion means the volumetric reservoir we don't have any of water. So what's the Campbell plot? The relation between F and the total. I can use this. Let's see. We can see here, this is the Campbell plot, give us a good diagnostic plot. What I can decision make from this plot. You can predict with me what's the case here compared with the last plot I generated. I will compare the Campbell plot with the last work here. No. Here's the next one. This is the case 1, case 2. No, this is the pressure, so I'm looking for classification. Yes, this one. Here in classification of this plot, I diagnostic this as a case in B. Maybe I am not sure about this decrease. That's maybe indication to water influx act as a finite acting, but in Campbell plot give us a good decision about that. So I can see here where is this plot? Yeah, I missed it here. I don't always when I create more plots here I miss them because where it's at, where it, yeah, really I cannot find them. I missed it here. Maybe I need to create another one, or yes, I think I put it here. Okay, I will again create this plot. Always happen like this. You have to be focused what you put. Yeah, sorry for that. Okay, in Campbell plot here, this is the Campbell plot. All right. Yeah, I can classification here this plot and this one. It's in Campbell plot indication about increase of strong water. We can see here moderate, that means increase some time, then decrease. But when I plot this Campbell plot, give us a strong water influx compared with the last C, because I was afraid of if water influx is act as a B, that means increase some time then decrease. I cannot say in this case that our water influx is high volume or have a strong water influx, but by Campbell plot give us a good indication about we have a strong water influx that's increase and will be increased, and that's a very very important plot. Okay, now I will do one more thing. I have more information about aquifer and infinite acting, as we can see here in our case. Case will be infinite acting. That means the water may be connected to the surface or any other sources unlimited. So always, if we have a good porosity and permeability, the more volume of water influx affecting on the reservoir performance. The aquifer configuration, maybe we have a bottom water aquifer and or edge aquifer or linear, and we can here from outer boundary condition act as an infinite acting. Now we have an indication about we have a water influx. So the next step is we need to calculate how much volume of water invaded into the reservoir from our calculation, because this is WE will affect on the of original in place. Until now, just only we have two values. One it's 6 billion stock tank barrel, and the next value is 200 million stock tank barrel. This is number is until now it's for our case more important than this number, so I will not depend on this. It's wrong. But also this number, it's with adding the rock and fluid expansion, but I need to calculate the next number. It will be more important than these two numbers. We're affecting by add a water influx value. So we will calculate aquifer model here using a simple one. We have many water influx modeling here. So you can see in water influx we have Hurst, Van Everden, and Vitkovich with both semi and steady, Carter, Tracy, and now I will use a small bot aquifer model using Excel sheet by using it's very simple equation. It will work with our case here, because I don't need to make that very complex, because I need to understand the basics of how material balance works and how can apply the history matching technique. But you must be understand what aquifer model cannot be used for just only this assumption of this method only for small aquifers here. And noting this model is independent of time. Yes, we can see here this equation depends on the water and rock expansion of the aquifers. So I cannot use this here or I cannot predict the right value of water compressibility and rock compressibility for the for our aquifer, because we have high uncertainty in this area. We don't have any wells in our aquifer, so it will be predicted and changed to then we compare that with our history matching. And also in this equation, independent of time, and that's mean when the pressure is dropped in our reservoir, immediately the water influx invaded into the reservoir affected by water and rock expansion. But that will not work with if we have a strong water influx, like in our case. In our case, when we have a huge volume or a strong aquifer, we cannot use pot aquifer model, because it will need a time. So in this pot aquifer model, we don't have any time. Maybe we know we can immediately have, when the pressure is dropped, how much volume invaded. That work with small aquifers. But when I have large aquifer, that means I need more time to invade it into the reservoir. So the time must be involved in the model. But that's the assumption of pot aquifer model. Other methods like Vitkovich and Hertz van Everden, if you see the equation, you can find the time, and that's will work with you. But here I will use this pot aquifer model to just only to see how can we apply it and compare it with if we don't have any aquifer. In this method, it depends on how much initially volume of water in the aquifer. We need to calculate the total, like original or place. We need to calculate the original or initially water in place. How much volume of water in the aquifer? By using this simple, we need to use aquifer radius and aquifer reservoir. The difference between them act as a ratio. Then I need to calculate the thickness, the thickness of aquifer. So if you can see here in Petrosoftware, I got many questions about this. Assume here reservoir thickness. That's not mean you need the reservoir thickness. In material balance equation, we don't see any thickness, but I need this number to calculate the water influx. Okay, that's very important about that. So all these we can check that again to see if I use small bot aquifer volume. What's the mean of aquifer volume here? It's need the initial volume. It must be first guess for the first assumption. We need to enter this value, initial volume. This is the initial volume in million, because until now we don't have any information about aquifer, especially this number. We know the reservoir radius, but we don't know the aquifer radius. The aquifer radius is out of reservoir radius and must be larger than reservoir radius. So I am not sure about this value. I don't know where is the end of boundary of aquifer, so it must be predicted here and initially calculated. Also the thickness. So if you enter, for example, here in Petrosoftware 1 or 2 million cubic feet, that means you use this equation to calculate the aquifer and porosity for this number, and then you can edit these numbers, and we will work with that in Excel sheet. And F factor, what's the mean of F factor? That's the encroachment angle divided by the degree of 360 degree. That's mean if we have affecting by the reservoir is faulting, or sealing fault, so you have to use the encroachment angle. Then after calculating this initially and the pressure difference between initial and after the pressure is dropped, you can calculate how much volume of water invaded into the reservoir. So I will start by calculating the initial volume of water in aquifer, applying this equation. So what I need here, I have an aquifer information, a reservoir radius, that's the reservoir radius, aquifer ratio equal to, that's the assumption. You must focus on this. What's the mean of 2? That's mean the aquifer radius larger than reservoir radius twice, or the size is twice an aquifer more than a reservoir. Okay, we cannot by using aquifer model, I cannot assume this value will be, for example, 10 or 20. Why? Because that means when I say 20, that means the aquifer size is larger than reservoir 20 times, and that's will not work, because a huge volume, a huge area of aquifer, that means we need more time for this. But here in this model, but aquifer, I don't need to use a huge volume, because if I do that, that's mean a huge wrong assumption. This. So also in aquifer radius, here in aquifer radius, that depends on this value. Okay, so if I have a ratio of 2, when I multiply by this reservoir radius, will give us aquifer radius. Okay, so here in I assume aquifer porosity, because I don't have any information about aquifer porosity, how the value, and the thickness also of aquifer I don't know, but I assume it. I assume this number and this number, and also water influx and rock compressibility, it will be assumed, and the encroachment angle 100 degree. 100 degree, that means our reservoir, if that's I can that's the I will assume that's our reservoir. Our reservoir act as a circle, so the reservoir radius from a center point here, this is the value, and the aquifer, it will be, that's the reservoir radius, and that's the aquifer radius. Okay, the aquifer radius, I don't know where is the boundary or end of aquifer. That's the water invaded into the reservoir from all of these sides or from part. So when I assume encroachment angle 100%, that means 100 degrees, sorry, that means I have a fault here, and that depends on the geological information. So if I assume we have one fault like this for our reservoir, and I can predict the water comes from this side, so the degree will be 180 degree, because this is the straight line, so this is the angle. And when I say 100 degree, that means I have 2, because it will be less than 100. So maybe the value of have 2 faults here, so this is the degree of water comes from the side, just only from the side. But I don't know if we have a fault here. I need to use, if I use 30 and 380, that means we don't have any fault, and the water comes from all the sides of the reservoir. Okay, so the first equation I need to generate here, it's this equation calculating how much initially volume in place. That means here's the water in this area, so I need to use this equation by minus r aquifer radius minus reservoir radius. So when I minus these together, it will give us the difference here in the aquifer volume. That's here, and we have oil, So, and here we need to calculate the initial water in place. It will be calculated by using this equation here. So we can see here, if I increase the angle, for example, if this value will be very, very high. Yes. Still I don't use any, so I need to use the fraction. Yes. Here in initial volume, and I need to use if it's very important, because it will give us where is the area or where is the side of water influx. So if I use for example the mean of water comes from all the sides, so the initial volume will be from all the sides. If I decrease this to 1, this value will be decreased for less than this number. That's depend on the fraction here of volumes. So now I need to use 100, and this is the first step. I have water, and I have rock reservoir radius and aquifer radius, and all of these information, porosity, and I can apply. Then I use modifying encroachment angle factor that I calculated, divided by angle, divided by 30 and 360 degree. Sorry, 60 degree. So I can use this encroachment angle divided by 360 degree. Give us 0.27778. If the encroachment angle comes from all the sides, so F will be equal to 1. I don't need to use it. Now I need to calculate the pressure drop at each step. Initial pressure minus P. Here I have the pressure data, so I can use initial. The first one, initial, will be fixed minus P. Assume the average reservoir pressure at oil-water contact. So I can see here the difference. The pressure is this is the delta B. Delta B means when the pressure drops, that means how much volume at each step of a pressure changes. So all of that, this equation affecting by the change of a pressure. Calculate constant K equal to rock and water compressibility multiplied by initial water. Then this is the total change in rock and water expansion, and that's the general equation. I need to use all of this. So I calculated here, multiply water and rock compressibility for our aquifer, multiply by initial volume, then using factor F. Yes, I don't need to use here F. Yeah, sorry, that's a mistake because I multiplied here. So don't do that if you follow my steps. If you use it here, multiply here, don't use it, but I applied here. The last step, I need to calculate the water influx, how much volume invaded from our aquifer into the reservoir. All of this will affect by change in the pressure, delta B. So equal K multiplied by delta B. First one will be equal to 0. Then I can have this number. What a mistake I made here. Oh, sorry. I have to K constant, does not change. Delta B just only. Yes. Okay, I calculate how much volume at each step we can see here this is the water influx at each point. So I need to use cumulative, calculate the cumulative, this number plus this number, I will get this. So plus, yeah, these two numbers will give us the cumulative oil, cumulative water. So this is the total volume of water invaded into the reservoir. I need to plot this with the I need to see how much volume. Okay, I can see now how much volume of water Pot Aquifer Model. A huge volume. I am very interested about these. Barrel, yeah, time here. Oh, I hope this can help me in history matching technique. How much volume, total volume of water I need to, how many million? Oh, yeah, still I didn't reach to 1 million of cumulative water, but about 915,000 of water. But I am very interested about how the curve like this water. Oh, I need to see how much the value of original place. That's okay. Now I have this assumption by using these methods. So what if I need to increase the value of aquifer porosity? Okay, maybe I need to use more. I need to assume more volume of water. So I need to use 0.20. So look with me here. Now the value, the last depends on the aquifer porosity 0.12. So about 915,000. So when I increase this, okay, oh, 1 million and yeah, 1.2 million. I increase it. Why? Because I increase the aquifer. So if I increase the thickness, I hope more. Oh yes, yeah, 3. Yeah, 3. The twice increase the aquifer from 50 feet to 100 feet. The value of water influx, the cumulative total at the end time, it's 3 million barrel of water invaded into the reservoir. So what if I increase the ratio to 2.5? Let's see. I hope more. Oh, more volume invaded into the reservoir. Yeah, 5.3 million. What if I increase the encroachment angle to be 200 degree? Oh, more than 10. Yeah, 10 million. So 10 million water invaded into the reservoir at the end of 2008. That's very good. I will depend on the first assumption about this, and I will use this plot now. So I need to calculate the last step after calculating the cumulative water. So I started by initially volume, F and delta B and K and water influx. Now I need to calculate the original place, the number 3. If you remember with me, graphical method, by using this relation, I will put this in Y and that in X, and the intercept will be the original oil in place. I will use this now by depend on these values. Okay, maybe I have high uncertainty in this value, but of course I I am interested about because in our analysis here we have from our aquifer, from our plot we decided we have an aquifer. So I will assume this result is good. So I need to calculate how much oil in place. What the next plot I need to generate here? Okay, maybe I need to use this here, or I will go back to here, add the case, adding water influx. What I need to calculate here by using this equation. So this equation, because I will add the water influx volumes. All right. So what I have in y axis F divided by total epsilon O plus epsilon and water. Okay, that's good. And what's in x axis will be water influx. I need to recall the water influx I have on this information. Yeah, that's good. So now if I have F here divided by plus both water, expansion of oil and expansion. That's good. Yeah, first one is equal to 0. All right, that's good. This number k will be 0, no problem. I have to, what's the value of cumulative? This is our value. I think must be converted to million. I will do that. Or WE model barrel. Here in F and okay, I don't need to change them because here I have barrel divided by barrel per stock tank barrel. So here in stock tank barrel and here stock tank barrel, no problem. Equal, sorry, so water, first one is equal to 0. I don't need to use water divided by plus of both total expansion. Good. I hope this plot can give me another different important information about my result. I need to calculate the original oil place actually. Oh, what's happened here? Yeah, I have to check my result before. What's in X? No, I need to use this here in X. I need to use the water, not this. I don't. I will delete the first number. So zeros, I don't need them in my diagnostic. That's and Y. That's clear. What's this graph method? Okay, I calculate in 3 or case 3. Water influx. But the plot must be This number is no. This plot doesn't give me any good information. But no problem. Yes, this is another different method. I will use it here. This Campbell plot with water influx. I can this plot can help me to give me the right value of original place. So if I can see here, if in analytical I got a good match, but when I see the graphical method, yes, I can depend on this method. This is the method I use it here, so I need to use this. Best fits give me the value of original place. So this is the same plot I did here. F minus E total divided by water influx and this number. So I am sure here I have a problem in water influx models, so maybe a very small aquifer model I generated here cannot give me a good direct decisions and indication about this. Maybe when I need to use the water influx to help me to give me a straight line like this, because here I use a different method of water influx calculation the water influx, so that's the good method. Still I have high uncertainty here. The value must be okay. That's the value of original place approximation, yeah. But when I see that in analytical, I can see the method is matched here with all the data, but I need to use a different method. One of them is Campbell plot. Yeah, Campbell plot can help me to give me the good result between these 2 points. So F minus E water influx divided by A total versus F. One of the methods I used before here in my case. I hope you get more benefit from these points. So now I am going to history matching technique. So how can I do that like in like this? So now I changed my result because I don't adjust my data or change it. So I need to go to my work here. So I need to understand how the method gives us. That's the material balance equation, the general one, and that's the analysis here in history matching. What's the advantage of using history matching? Is I'm not sure about my aquifer parameters, so consists of modifying the aquifer parameter must be acceptable by our matching. So I am using here that's my wrong decision or my wrong predicted for my value here. So that will be I will use this. So if I assume now this value is right, the aquifer thickness, or my case here, sorry. So I will be assume my result here it's very good, and I get the good result for encroachment angle and water and aquifer thickness and water compressibility, all of these information, and my result here is very good. Okay, so how can I confirm that? History matching. So if my numbers here very good, when I plot this with a history matching technique, it will give me a good result. If not, that means I have a problem with my data. I need to rechange. I need to change these parameters and calculate another water influx. Then I use it in history matching technique to compare that. So how can I start my work in history matching? That's our task. So this is the analytical method. That's the general form of material balance equation. So I am now, if I confirm the good value of origin or place, I can need to calculate the cumulative oil production. So I have the observed data for cumulative oil production from our field. That's the measured, and I am sure it's good and consistent and accurate because it's measured at each well, then calculated as a cumulative. So if I use this equation, it's from this equation, it will give me calculate another different value for cumulative oil production. This value depends on one. This is the calculated depends on the original value from our field and the BVT and the water influx. And here is the calculated by Pot Aquifer Model. So if your prediction of water influx is good, that will be, this value will be good, and we will compare that with our data in the field. So all of this calculation depends on this value. Okay, so that's if you get the good indication about the good aquifer parameter, then you will calculate the good water influx model. Then you will get a good result. How can I understand and how can I configure this? By get the same data with here in matching. Now I can show to you I need to calculate the pressure versus, this is the general and accurate data I have. Oh, sorry. That's the last task for today. Yeah. In X, it will be cumulative oil. This is the right value of cumulative oil calculated from our field. And what's in Y? Pressure. Oh. Okay, this is the observed data. Okay, here in y-axis the pressure, and in X oil production. This is the good result I have here, so I need to add another curve. Okay, so the first step, I am working with the history matching without water influx. So depends on this equation, I will assume no water influx invaded into the reservoir and apply all of these parameters here and calculate the cumulative oil production. So I apply this here, no water influx. I use this equation and calculate the cumulative oil. So I am now need to use, this is the pressure and, oh sorry, I will add them on the same plot. So I have pressure and the cumulative oil production for my field, and we'll add a new one. It's called NB, cumulative oil production without aquifer. What's in the X? Cumulative oil. This is the history matching like in Petrosoftware. So I assume no water influx and the pressure measurements, it's Okay, I have, yeah, what's happened here? No match between the pressure, no match between the two curves here. We can see the cumulative cumulative oil production. It's about 3.7 million stock tank barrel of oil at the end of this time. And if I assume the reservoir is without aquifer, so I have I don't have any good information. It's low volume of water, so no match between two curves. I have good data. So now I need to add another. What's the next step? Now I need to use another different curve. It's called with aquifer. So in the next one, I need to use calculate the original calculate the cumulative oil production. Depends on the value of original in place. That's the best value for me. About 10 million stock tank barrel, and I have rock compressibility and all of these information. So again, I will use the same equation calculating the cumulative oil production, but add water influx volume as I calculated in my aquifer model. So I get the cumulative water. Here I have water model. So maybe I can use the same for cumulative oil. I will copy these values. I get this data from my case here. I will put them here. Oh, sorry. Yeah, then I convert it to million because I need them here in million. So now I calculate the water influx by using calculate the cumulative oil by using water influx. So cumulative oil with water influx. What's in the X? Cumulative water. And in Y, pressure. Yeah. I can see here I have a huge volume of water invaded into the reservoir. I cannot trust about this result, but you can work with them. Maybe here I need to see the value of, yes, about 13 million, a huge volume of oil in place, and that's not right, because the good result I have for my data here, it's about 3.7, and that's a huge volume of water predicted by the water influx model. Why? Because I increase a huge volume, a huge parameter here, so I need to decrease the encroachment angle for B1, and also the thickness will be 4.5, and maybe I need to use aquifer 0.12. Okay, so now I have the cumulative water. I reduce the aquifer properties, so the less volume will be increase here, decrease. Yeah, I can. Oh, again, my data here still I have low volume. I assume here, if you can see here, the two lines here with cumulative without aquifer and without aquifer are the same. Why? Again, because I decrease the low volume of water, so that gives me the, instead of water influx, less volume that no have high effect. So I need to use this again, and that's how the Impel software works, because it's a software and speed for this calculation. So again, oh, I made a mistake here actually. Why? Because okay, so now I can see this is the good match between my data. I assume I am very happy to get this result because maybe I do that, but when I am recording I am a little bit afraid of getting a good result. So I'm so lucky to get a good result to show to you, because if I don't get a good result here in recording, maybe someone say, no, you don't understand the basics and how can it work. So yeah, that's good. That's not very good and good matching, but it's okay. I can change the pressure for to be more clear, yeah, or I can increase more. Yes, still I don't have a good match, but acceptable to if now I am understand this is the actual pressure measurements and the cumulative oil from our field. This is measured, and this is the prediction of my data. So now I still have high uncertainty because I have don't have a good match. But if you can now imagine with me, if I decrease the properties of aquifer, for example, I need to do that right now to reduce the volume, because here that means the huge volume at this point. For example, at this pressure point, we can see a huge volume of oil production, much higher than the actual pressure, the actual oil cumulative. So if I decrease the aquifer radius to 1.3, okay, then I need to decrease this to be 1. I will yeah, small changes here to see what's happened with matching. So the process is trial and error, so you have to change and see the result. Yeah, this volume I need. Okay, I will use this. Yes, huge volume changes, and so I need to calculate again. Yeah, I am between high and low, so you have to get the best value between these. Yeah, okay, maybe you can use it to because you have high uncertainty, so you have to work with sensitivity analysis to help you. Yeah, you can see with me, after increase the aquifer thickness, so I will use it to 1. I will see the changes here, so maybe I am very close to get a good match. Let's see. Yeah, so maybe I can increase more, or some changes here, 1.8. all right, let's see what's happened with the small changes. And yeah, you can see with me, you can add some changes to see the match between aquifer, and but this without aquifer it's not acceptable. anyhow, you have to work with Aquifer model until get the best match. That's the end of this lecture. Thank you for joining to our channels and in Telegram and Facebook and all of our social media platforms. Thank you so much. I hope this lecture can help you so much understand the basics of material balance using Excel sheet and use the mathematical equations. How can we apply it and understand the graphical methods we generated here for case 1, case 2, and Campbell plot and classification. I hope you get more benefit from this lecture. Thank you for joining to us. If you don't subscribe our channel, you can do that now. Thank you so much. See you in the next.